Okay, good morning all. Yeah, it's not quite yet time to start, but just so that you know, I actually discovered accidentally this morning that I dress like golfer. My shirt is exactly golfer's color. Okay, so if I do this, then I'm pretty much like golfer. Yeah. Oh, hi, good morning, Jia Hong. Yeah. So you know what? Before we start, maybe I can bring up the schedule. We are in the third week. And PA2 is due, as you are reminded already yesterday. Oh, Yun Tong, that's probably not good. It's very nice of you, 见物抒情, or actually I learned who you are yesterday. Wei Yuan, right? Oh, that's very nice of you. Hey, carry Polly sometime. Yeah, golfer. And this is the third week, PA2. I have no time to stitch something like this up. I just discovered that the color of the shirt is exactly golfer's color. And there'll be just 3 more weeks until we have the first exam. Okay, and Polly is getting better that Yun Tong had a big question mark, so hey, Wei Yuan, you are challenged somehow. All right, so good morning, Catfish, Zhao Qi, and Doris. Yeah, you're the exchange student. I hope that the course is so far so good. And Amelia, good morning. All right. Yeah, so in case Yun Tong is asking why I was joking about the color of my shirt, yeah, now you see, Polly's shirt's cover is exactly golfer's color. So I was doing this there, and I look pretty much like golfer. All right, good morning, Ziwei and Shen Hao. Let's go ahead and start. It's being, oh, that's really nice of you. Okay, Doris. And if you follow the end of yesterday, we'll start today from quiz 6. Okay, so this is essentially the topic list for the first hour. And we'll come back to work on quiz 6, which is right here. Q1 and Q2, you know, quite straightforward if you follow the video. So why the 3 measurements, okay, for each of these hops? The numbers are different, right? So we see 2 millisecond, and then for some other hops, for example, hop number 10, the delay was 113, 121, and 114. Okay, so we measure the round trip time to the 11th hop router. But the measurements are all quite different. Why? Q2, how come some delay measurements to hop number 10 are longer than the delay measurements to hop 11? Supposedly hop 11, right? 11 hops away, okay, should take longer time. But the delay to hop number 10 can sometimes be longer than the measurements to number 11. Why? And Q3 is a little bit tricky. If somebody asks you to estimate the delay from hop 3 to hop 4, so the time it takes to send the data from hop 3 to hop 4 router, how long it will take? How can you exploit trace routes output to do that? Now, the real tricky one is this. Can you estimate delay between hop 8 and hop 9? And you know what? I have already discovered that many of you have tried to answer quiz 6, given that the questions was posted yesterday. Okay. So Sean, team 1, always the first. I like students being aggressive. So team 1 here is saying for Q1, because the 3 packets might go through different paths. Okay, this is very good observation. I think in the video we showed yesterday, right? Polly tried to demonstrate using trace route, okay, from Polly's remote login client, from Polly's terminal, and we see if I trace route to www.google.com, I actually might go through some hop where I can use 3 different routers for hop number maybe 5 or 6. So even though I send the traceroute packets to the same destination, but these 3 trial that I'm sending packets out can go through different paths indeed. And therefore the delay very reasonably can be different. But Team 1 also say this, even the 3 times the paths are exactly the same, there's also what? Queuing delay, right? We were talking about delay and what are the 4 components in delay. There's something called queuing delay. We spend a little bit more time. And because internet is what? Packet switched. So we could have packets coming in too fast, then the router will be able to send them out because the outgoing link capacity might not be high enough. So those packets coming in really fast might need to wait in a queue. So there will be queuing delay, and the amount of queuing delay can vary depending on what is the traffic composition at the moment, right? That traceroute probe arrive at that hop. So this can be a little bit random because you don't know how other sources are sending data. And that's why in 3 trials, even the paths are identical. At different time, you're sending these traceroute probes. Delay come up differently. So there's a queuing delay there that creates uncertainty. Processing delay usually somewhat consistent and negligible. Transmission delay, whatever the link speed is, it's pretty much fixed. Okay. Propagation delay, if the transmission speed and the cable that you're using, okay, the modulator at the 2 ends of the cable are fixed, then that propagation delay is also the distance from the sender to receiver, that is also fixed. Then the propagation delay is also fixed. Okay, so propagation delay, processing delay, transmission delay, pretty much fixed. Queuing delay is in fact the only component that's varying, and it can vary quite a bit depending on the traffic, again, composition at the time. Okay, the packet comes into the router. For Q2, as we said in Q1, it might be the path that number 10 router takes. Oh, I see. Yeah. So the path, okay, hop number 10, okay, at the time could be busier than number 11, right? Therefore, the probes to 11 ended up having shorter delay. But one of the probes to hop 10 might be experiencing significantly higher queuing delay. Therefore, the delay turned out longer. Okay, now that explains also Q2. Q3. For the delay between hop 3 and hop 4, they would do it this way. Let's see. Okay, I think team 1 is what? Subtracting the delay to hop 4 to hop 3. So it's 16 subtracting 6. Let me see. 3 and 4. 3 and 4. So the first delay is 6 to hop 3. First delay to hop 4 is 16. So they are subtracting, okay, 16 to 6. And they do this for 3 times because they are 3 trials. And take an average. All right, so that's one way of doing it. This will be then like the average delay between hop 3 and hop 4. All right. Oh, and hey, they are careful because A millisecond is the round trip between 3 and 4. So they divide it by 2, one-way delay. Very good. In 8 and between hop 8 and hop 9, although it has busier background traffic. Okay, very good. Yeah, so composition of other traffic, that's exactly called the background traffic, right? We think we can estimate the delay that happened is 109 subtracting 104 divided by 1, which is 5. Oh, very interesting, very interesting. Yeah, the reason that the second part of the question is a little bit trickier because you see here between, which hops? Hop 8 and hop 9. Between hop 8 and hop 9. So hop 8, first trial, we have 104, 109, makes sense, right? Hop 9 there, the round trip delay 109. Hop 8 round trip delay 104. They subtract and get the difference 5. Okay, and they divide that by 2 as an estimate of the delay between hop 8 and hop 9. And I guess the reason that they discard the second and the third is because, 109 round trip delay to hop 8, the second trial, is higher than the round trip delay to hop 9, the second trial. That doesn't make sense. Okay, so obviously the queuing delay here is not quite like the queuing delay here, down going to hop 9. And they thought that they might need to neglect these. Okay, otherwise they get a negative value, right? How can delay be a negative value? Yeah. So I guess for team 1, to estimate the delay between hop 8 and hop 9, the algorithm is check. Okay, delay to hop 9 and hop 8. If hop 9's delay is higher, then take that and use it as one of the values they average. All right, that's one way. That's one way. But I don't know about you, right? Poly will then feel a little bit uncomfortable averaging just one value. So Poly will probably do multiple trace routes so that we get more of these values where round trip delay to hop 9 is higher than hop 8. And then we take multiple of these and average. All right, let's see. Jimmy came in very early today. So Jimmy was the one arriving the first today. I guess you are here because you want to work on the quiz, isn't it? Very good. Oh, very morning person that gets a sunflower here. Q1 says, because routes may change during a session, definitely. Even if the routes are the same, there could be a queuing delay that's not exactly predictable, depending on the background traffic. The load of the internet exactly is changing all the time. That's why when we probe to a closer router, but the queuing delay is higher, then we ended up having a higher round-trip delay than the round-trip delay to the farther away router, sometimes. Okay, I see Team A is taking the same approach, estimating the delay between hop 3 and 4. Okay, also the same for hop 8 and 9. Very good. Team 4 here, Jason is saying the queuing delay might be different. The path can also be different. Now you probably can see, right, generally the two reasons for these delay measurements being different. Path and queuing delay. Okay, path can change from time to time. Queuing delay changes a lot more frequently. It is possible for the delay to hop 10 being longer. Yeah, for the same reason, queuing delay. It really depends on the background traffic at the time. Okay, we are taking the measurement. Q3. Yeah, very similar to Team 1's solution. Let's see, Team 7, Liang Zheng is saying, if they travel the same path but traveling at different time, there could be different queuing delay, exactly. Okay. Between hop 10 and hop 11, yeah, so the three measurements to hop 10 might be experiencing more background traffic, right? So the traffic might be heavier then we are taking measurements to hop 11. Sorry, excuse the noise from outside. I had a directional microphone here. Hope that you don't pick up all that much of the noise there. 3. Okay, so this approach is a little bit different. I think Team 4 is taking this approach. So you don't necessarily subtract hop 4's delays to hop 3's delay in pairs. So you kind of add the three values together and average, okay, and then subtracting the other three values and average. So this is slightly different, okay, from Team 1, Team 2's. Okay, Team 1 and Team A's solution. Okay, so Team 4, Team 7, there's a slightly different way of estimating the delay. And so you probably see that are the delays different? 4 milliseconds? Oh, actually, the final result is the same. Let's see. For Team 7. Oh, interesting. This is a very keen observation. Between A9 and A8, Team 7 is careful. Okay, instead of saying that, hey, the delay estimate is 2.5 milliseconds, they say, well, the delay is less than 5 milliseconds. I mean, the round trip delay is less than 5 milliseconds. So to be exact, it's a little bit hard to know. So I guess the curly sign there is just, approximately something like less than 5 milliseconds. Okay, so Team 7 likes to be articulate. Okay, 梁正, good for you. 右鱼, let's see, Team 14. Depending on the congestion level, okay, this is a very good way of saying the same thing. Background traffic can be high-low. That means congestion level can be high-low. Yeah, we talk about this term, right? Packet switch network does have packet contention. We also call that traffic congestion. Well, the same thing we call the vehicular traffic these days, don't we? Last weekend, it's a long weekend. Yeah, there's congestion on the freeway on Monday. Okay. So total delay therefore can change over time because the queuing delay can be different when there is congestion. Similarly, the reason that the delay measurements to hop 10 can differ from can be longer than the delay measurement to hop 11. Number 4, average. Okay, so you add them up. Oh, interesting. So you add them up, average, okay, for hop 4, and you add the measurement to hop 3, add them up and take average, and then subtract. Okay, so average round trip delay to hop 4, average round trip delay to hop 3, and then subtracting them. Yeah, we understand. Yeah, so for hop 8 and 9, it's a little bit tricky, isn't it? Yeah, because the second pair of measurement, third pair of measurement, you see that the delay is probably unreasonably high. So you don't get the normal delay when there is no congestion. Okay, very good. All right, rocket here. 云筒. For 3 different probe, measurement can be different. And let's see. Probing to a closer router will be more because it may be busier. Definitely. Okay, so you are also doing the pairwise measurement and then average. Yeah, because they are negative, so you ignore the second and the third for the delay between hop 8 and 9. All right, makes sense. Oh, yeah, definitely. Brain power there. Yeah, and I think Yuntong is carrying you this time. All right, let's see. I guess the rest of the team, the answer now you see we are converging for Q1, queuing delay, and going through different paths, 2 possible reasons. Some of you guys say both, some of you say one of these. Either way is fine. And in fact, the reason answering Q2 is exactly, it could be because of different paths, it could be because queuing delay being different at the time we are taking the probes. We also see, right, the mechanisms also somewhat similar. Let's see, queuing delay, definitely. Right. And congestion also, at the time taking the measurements can be different. there we go, very similar. Between hop 8 and 9, you take shorter delay from hop 8 and longer delay from hop 9, maybe. 先好, let's see. Yeah, very good. Okay, so you guys have got it. And so we can move on. So far we just talked about one measurement metric to say whether the network is working well or not. Okay, typically shorter delay, the better. There are two more metrics. One is loss. We don't like packet losses. Okay, usually that means you miss some information or it takes more time to try to recover from the lost packet. Second is throughput. This is how much traffic we could actually send through, push through the network. Okay, so let's talk a little bit more about these two other metrics. First, loss. It's very short because it's quite straightforward. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission. Throughput is the third metric. And it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end. And the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other, average throughput. Now, the units are both bits per second. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the slides will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see, I'm drawing, okay, the pipelines with the diameter based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an end system, this is an end system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay? Most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services. All right, so those are the 3 metrics. Nowadays, delay is the more that the users care about. And now we move on to the next subchapter in chapter 1. It's called INET service model, but what really we want to talk about is how network engineers can manage all these software pieces. 1.5, protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called Something Layer, Something Layer, Something Layer. Okay. We kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do. Now, let's recall all the terms we've referred to since the beginning. Right, Oopsie, sorry, probably misclicked the video. Okay, so let's go back. We are not yet done with that video. 1.5, protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called Something Layer, Something Layer, Something Layer. Okay. We kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize softwares running on the internet. Now, let's recall all the terms we've referred to since the beginning. Right, we've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right, the other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links that operates different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing that makes the internet work magic today. A lot of times we rely on these applications in order to what? To see a page that we are looking information from. Okay, so applications such as World Wide Web email, and these applications a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay, and these are client and server side will need to communicate based on a specific rule. Okay, and so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay, so this is one example of the software on the internet, and there are a lot of these softwares. Okay, and application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay, is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also for the incoming network engineers and how the senior ones teach the junior ones. Okay, and so let me explain why layering by using an example. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here, I meant the service model, the way the service operates. Good. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also a C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay. So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport and this is at the arrival airport. Okay. So you see that there are components that are related and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here, well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different. But these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end. Communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay, so to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three, okay, are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the day or change the class, okay? And the reference is always, for example, the ticket number, okay? So for communication, you need certain important IDs, important information there, okay? To communicate within a layer, okay? The claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay. So we see air travel, okay, is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Okay, each layer implements a particular function. Okay, a particular subservice. Okay, and so there will be some internal actions, but they will also depend on services or functions provided by the neighboring layers. Okay, from the layers below, okay, or they might also need to provide supports to layers above. Right. So that's why internet protocols are also organized in layers. Internet protocols, the software system itself is also a gigantic complex system. Okay. Hopefully with the air travel example you see, in large complex systems where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right. So after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay. So that is called modularization. Okay, this is really common we see in large software systems. Okay. Because it's a lot easier to maintain. It's a lot easier to debug problems. And it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay. And that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules. Okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers are minimal. Modularization, or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good? All right. And I guess that you are more comfortable that we always talk about internet protocols in layers: application layer, transport layer, network layer. Now let's take yet another look of the layered internet protocols. Here's the internet protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are, okay, literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the web browser side and another application layer process at the web server side. Okay? And there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines, right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. Okay, the functionality is essentially to allow these application layer protocols to specify, okay, whether these data that I'll be sending through, these data packets I'll be sending through the internet is going to be reliably transferred or best effort transferred. Okay, so this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. Yeah, all these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right, needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, okay, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. Okay, so these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Okay, transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer, but it's between one network element to another one network element, one network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. Okay, so this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. Okay, so it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol. All right. And next video, it's very important because what Polly will do is to show you how data gets traveled, how data travels through the software layers and across the hardware components. And in each hardware components, traveling the software stack a little bit more into the next hardware component. Okay. Now this video, unfortunately, is a little bit longer than the time we have, so we'll run over for a couple minutes. But we'll take a 10 minutes break, so you won't lose time. I'm just moving some of the time in the second hour to now. So this video, pay attention. With the layered architecture explained, what I'm showing here is the software side of the internet side by side with the hardware of the internet. So where are the hardware in this example? Look, here, and here, and here. So these are end systems. Okay, this one is the source, and this one is the destination. You see that at the end systems, the entire internet protocol stack is implemented and running. Similarly for the other end system. But in the core of the internet, you see the router over here. And this is a very special entity, hardware entity. It's called switch. But to be precise, this is the link layer switch. Its functionality is limited. Okay? Unlike router, this is a network layer device that implements the protocol stack from the lowest up to the network layer. The link layer switch is a more limited device. It implements only from the physical to the link layer. Well, then you see how it gets the name. It's a link layer switch. And if you want to be precise, you can also call these routers the network layer routers. Or sometimes we actually call these routers network layer switches. Okay, so both of these entities are doing switching, but doing the switching at a slightly different level. All right, now walk with me and let's see how the data gets passed down the protocol stack, out of a physical entity, and through the network, reaching the destination. The first step is this. Yeah, one particular user typing things up. So at the application layer, this component generates a message. Yeah, a packet at the application layer is referred to as a message. The application layer component will pass the message down. As the message arrives at the transport layer, a header is being appended in front of the message. Okay, because it's appending, therefore, these additional pieces of information is referred to as the header. H stands for header. And this is a header appended by the transport layer, therefore HT. The whole thing together, this packet, is referred to as the segment. So a packet at the transport layer is called a segment. And you see that this header here is very important. This is to allow the transport layer component at the source side to communicate with the transport layer component at the destination side. Okay, so this is a little bit like at the airport when we're checking our bag. The counter is going to give us back what? The passport, the e-ticket, and what? The baggage claim ticket. Okay, so that baggage claim ticket, that additional information, okay, in order for you to find your bag, is a little bit like the headers. Okay. And now the segment is going to be passed further down to the network layer. And guess what? The network layer component is going to append some more information to it. And that is in the header as well. But this is the header for the network layer, HN. And the whole thing now, the packet here at the network layer is called a datagram. And the whole datagram is going to be passed down further to the link layer. And guess what? The link layer header is going to be appended, and we call a packet at the link layer a frame. So this frame here, now arriving at the physical layer, what physical layer is doing is simply modulating the 0 and 1 bits, okay, onto the physical media. So it's going to go out shortly through the network interface and arriving at the router here. Now I'm skipping the switch here because it's a link layer device. We'll not be able to cover the link layer chapter. So this message is going to arrive here at the router, receive at this physical layer, and the signals gets converted to the digital form. So we restore the original frame back, and that's passed up into the link layer. The link layer at the router is going to examine this header and see if there's any additional function that it needs to perform. When everything is done, guess what? Okay, this header is going to be removed. So only the message with the transport layer header and the network layer header will be passed up to the network layer. You see here, the message is being passed upwards, okay, because the network layer component of the router still needs to check this, okay, and see if there's something that the network component needs to do at the router. So this is going to be examined, okay, and functionality is performed. Now this part, hey, as this is a router, there's no other layers above, so this is going to be copied over, okay, and stand by there at the outgoing interface. Now before that message go down to the lower layer, the new network layer header is appended, and this one is a datagram. It gets passed down to the link layer header appended, and this is a frame. It goes to the physical layer, bits modulated, traveling the link and reaching the destination. Similarly, the physical layer is gonna recover the 0 and bits and give this up to the link layer. This checked by the link layer, and the remaining gets passed up to the network layer. And you see this removed, this part gets passed up to the transport layer. This removed, and this part here gets passed up to the application layer. And here, the destinations processed there at the application layer, finally you see the message coming from the source originally. So this is how a message travels through the protocol stack and the physical infrastructure, and more protocol stack up and down until all the way up to the application layer and the destination. All right, so that is like the life of a packet coming from the source to the destination. In a nutshell, it's a very simplified view. All right. Oh, Guan Yu has a question, so maybe I can address the question, but the rest of the class, feel free to take breaks. So we have 11:13 right now, so we'll resume the lectures at 11:23. Okay, so Polly then in the meantime try to address Guan Yu's question. Although we skip switch, does it also remove headers and then append a new one? Oh, the link layer header. Yes, it does, Guan Yu. That's a very good question, because the link layer header coming from the source, okay, to the first switch, the link layer switch there, that's one kind of link being used. And the link layer header, exact format depends on really the link layer technology. So if it's an Ethernet link, then it will be an Ethernet link layer header. If it's Wi-Fi, then it will be a Wi-Fi link layer header. Therefore, you see that from that link layer switch to the router down in the example earlier, that link can be something else. It could be an optic fiber. Okay, so for that kind of link, we could be using a different format for the link layer header. Yes, we skipped the link layer switch, but link layer header gets replaced indeed. Very good question. So all of you go on and take the break. So let me move to the opening side. Okay, a little bit chit chat before we start. Do you think that we'll be able to travel freely after summer? Yeah, Polly can't wait to travel. But Polly dislike that even in Taiwan, we need to kind of come back to Taiwan and stay in the hotels for 2 weeks at least to get out. Yeah. Well, you know what? It's time to restart. So this is the structure of topics we'll cover in the second half. And we'll start by opening chapter 2. It's a quick overview of everything. I think we can travel freely. I hope so, Liang Xin. I hope so. Okay, so, fingers crossed. And overview for chapter 2. It's actually not a short video, but I think it's a good thing to give you an overview of the whole chapter and to setting also some background. Flow of chapter 2 is this. We'll start by talking about the design principles, particularly how one designs the application layer protocol for data transfer in an application. Second, we'll go over a number of these popular applications as examples, okay, and demonstrating how we exercise these design principles and coming up with the application layer protocol for each of the applications. So HTTP, how it's designed to support web page transfer. FTP, the protocol to support file transfer. And these are the protocols to support email transfer. DNS here is to support transmission of hostname to IP address mapping. So a lot of time when we request data files, we actually give it a hostname. But messages on the internet do not get to the destination by knowing the hostname. They actually get to the destination by knowing the IP address. And therefore, for every messages you send out, we need to translate from the hostname to its IP address. So DNS is an application that we use every day and frequently each day. P2p applications, usually not all of us have experience using these P2p applications, but they are quite popular these days. For example, BitTorrent, for example, Skype, for example, Bitcoin. So the way data are being transferred on P2p applications is quite different from the more traditional applications such as web email. So in the traditional applications, we do it more client-server way. Someone asking for pages and server returned with pages. In P2P, each of these computers involving the communication, the roles are actually equal. One can be providing services to each other. One can also be requesting services from each other. Okay. There's a certain advantage of transmitting data this way. We'll see when it comes to 2.5. And then multimedia applications. So by multimedia, I actually meant video, okay? Transmission of video. You see that video, quite different from the content being transferred here. So web, file, emails, these are all text-based. Video is a very different type of content. So if you think about it, video is a stream of picture frames. Okay? So the volume of data is by default higher. And these frames need to be streamlined through the network so that they arrive one after another. This is to ensure smooth playback of the video. That's why when we say video transfer, we don't quite say the video transfer. A lot of time we say video streaming, okay? Streaming applications. And because of the nature that these video content, we do have short delay requirement. We do need more bandwidth to transmit higher volume video content. When we talk about multimedia applications like videos, we talk about this, CDN, Content Distribution Network. So this is a network of content servers. Okay, these content servers, usually there are multiple of them, and they are placed here, there on the internet, and hopefully close to the video users, to the video consumers, such that the delay will be short. Such that the segment of network is small, therefore you run into less bottlenecks, therefore the throughput or the bandwidth, effective bandwidth is higher. Okay. So video streaming, and this very interesting way of designing a video application using content distribution network. So these will be the key content we talk about in chapter 2. We'll skip this, socket programming using UDP TCP, because in the PAs, the practical assignment or programming assignments, in those videos, you will see how we do this using Golang socket. To make sure that we're in sync, let's inventory some of the popular network applications here. Email, web, nothing more need to be said. They are obviously email and web. Text messaging, Line, WhatsApp, what else? A Google Messenger. And if you guys are watching this from a YouTube live stream, that chat room is a text messaging app. Remote logging. If you downloaded a client to remote logging to the PA server, then you're using a remote logging application or remote logging service. P2p file sharing, the most well-known one, BitTorrent. Multi-user network games. Okay, so this is a more formal way of calling online games. Okay, so some of these online games are running on desktops, going to the game server somewhere provided by the game company. The client can be nowadays running on smartphones. In fact, probably more games people are playing are mobile games. Okay, so the client is on the mobile platform. And then the multimedia applications. Here we have the streaming stored video, and we have the real-time voice. So this is also called the voice over IP. And we have the real-time video. Okay, well, real-time video conferencing, of course, also comes with audio. Okay, so essentially these three are multimedia applications. The difference between this and these other two is that the video is actually a playback video. So the video is already stored in one of the video content server, and when you request it, it is just playing back the video. But for these are the live video being generated as you guys are having conversation, as we are having conversations. So the delay requirement for live audio video is a little bit higher, more stringent. So what do we have as real-time video conferencing apps? Yeah, Google Meet, the one we have standing by here, allowing you guys to call in, is a real-time video conferencing app. So there are other real-time video conferencing apps such as Zoom, Microsoft Teams. What else? Well, Skype. Although transfer audio, it also transfer video. So Skype is also a real-time video conferencing app. So there are many options here. Social networking. Hey, Facebook, IG. One can probably come up with others such as Snapchat. Yeah, so there are just increasingly more of these social networking apps. Search, Google Search or Bing. Yeah, each of these is also an application or a network service. Cloud computing, yeah, Amazon AWS, for example, is a cloud service. Now, to support all these applications, the principle is quite straightforward. Essentially, we write programs. There involves at least two parties. One program sits on one of the parties. Particularly, each of the programs sits on each of the end systems involving the communication. Okay, so they will be communicating, sending messages over the internet. So for example, web server program sits on the web server machine. Browser sits on the client machine. And these two programs send messages to each other. Much like this. So we might have a web client here. We might have another web client here. And the web server is down here. And we establish connections like this. So this client's program interact with the server's server program. This client's program interact with the program running on the server as well. Okay, so you see that the server program here needs to be a little bit more powerful, allowing requests from these clients, okay, frequently and potentially simultaneously. So essentially, in order to create these network applications, we design how the messages are exchanged, meaning designing an application layer protocol. Afterwards, we program the softwares. There'll be one part running on one end, the other part running on the other end. So this example here is a client-server application. For P2P, one runs on peer, the other runs on another peer. But in P2P, these two programs usually are identical because they are both peers. Now, what's unique here is this. Applications run only on the end systems. In the network core, the routers do not run anything particular for a particular application. Okay, so the core devices do not run applications. They do not run specific functions to support individual application. Okay, so applications are strictly on the end systems. So clients, limited devices such as a smartphone, such as a laptop or desktop, are on the edge of the internet. But you see here, servers, more powerful machines, they can be quite expensive. Some of them can be just as expensive as the routers. But these servers are also at the edge of the internet. They are also end systems. Just don't be confused. Okay. So these end systems, there are programs running and exchanging data such that we can perform a specific application or specific service. All right. So one very important point there Polly would like to stress is that the application programs run only on the end systems and not in these core machines such as routers. Because if we want to improve these applications, all we need to change are just the programs running on the end systems. And for these laptops, desktop servers, it's actually easier to lay our hands on. Okay, but routers, okay, these expensive machines are usually in major data center. It's really hard for us end users to get access. Okay, so applications, let's move it to the edge so that we could quickly evolve, okay, progress the development of the applications. Core machines that keep them stable and not changing all that frequently. Okay, otherwise, if you bring down a router, the internet for that part, for that region, might be interrupted for some time until the routers are brought back on. Okay, so applications. In fact, if the functions are considered that we would like to change, very likely in the future, push it to the edge. Okay. And that takes us to quiz number 7. All right. So this quiz is actually more serving Polly's purpose. Okay. So every year, I survey the young generation about what you guys are doing using the internet. Okay, so this is to prevent Polly from out of sync of the society entirely. Yeah, so Youyu asked the question, what make you think of traveling suddenly? So Polly travel extensively, and Polly likes to travel alone. So I was constantly seeking solitude. And not being able to travel. Okay, so being constantly with the family, sometimes you get a little bit nervous and you feel too much responsibility here on the shoulder. So traveling is a way that I can let go of everything and then just be myself. Well, hey, guys, you're free to be yourself and tell me, okay? Because a nice thing that Polly teaches in college is that I have access of you, the young generation. So here it goes. Q1, please tell me the top 2 applications you use that involve the use of internet when you're using a PC or a laptop. Okay. I mean, the PC, if you use Mac machines, then of course the Mac PCs. Okay. Q2, the 2 most frequently used apps when you are using your smartphone. Mm-hmm. You might see that the apps you use when you are sitting in front of a table, okay, might be different from the apps you're using on a smartphone. And Q3, 2 games, the most played games recently, okay, and it can be on any platform, okay, PC or smartphone. Okay, sorry about that, Youyu. Well, it's okay. Q7, let me go to the Slack and post the question so you can start typing up, okay? The top 2 apps, if you are using PC or laptop, the top 2 apps when you're using smartphones, and the top 2 games across all platforms. Okay, okay. I see maybe there's a little bit of struggle here because you guys are working in a team. So some members might be using these two apps when they're on PC. Some members are using other apps when they're on PC. So feel free to type up, okay, on behalf of yourself, but in the meantime for the team. And the other members can actually add by replying to the post for the team saying that, hey, I actually use different apps. Okay, so hey, don't argue. Okay, so you can actually add a pen to the post, appearing that it's for the team, but you can add more to say more about your personal preference. Oh, wow. Okay. Very interesting. Very, very interesting here. Okay, so team 8 again first. Jimmy. Very good. Line and the score are the apps you use on PC laptop. Okay. And IG and YouTube are the apps you use more on smartphone. And the two games. Okay, LOL, I know this is a very popular game in Asia in general. And maybe also the rest of the world, but particularly Asians like LOL. Overwatch, I've heard about this game, but sorry, I have to Google it up in order to know better. And Team 3, Yun Tong here, again carrying Wei Yun. Facebook and YouTube, okay, good. So social networking. I guess Discord is also a little bit of social networking, right? You kind of need to have like a community there. And IG, of course, and Line. Yeah. And yeah, so this game, I just look it up. It's a shooting game, I guess. You probably also form team, right, in the game, I guess. A little bit like PUBG, but the formation is different. It does look a little bit more like it's a role playing plus action. Yeah, I think nowadays many of us like RPG action hybrid game. Brawl Stars. Okay, so let's not look up all these games too much here in the class, all right? So Yun Tong, I'll definitely look up this other game that you're playing. 良心? YouTube, definitely. Discord, play with friends. Yeah. I guess when you're playing like team sports games, you do need to communicate a lot, right? So Discord is real-time audio. All right, so one of these multimedia applications we were mentioning, Skype is one, but nowadays I guess all the young generation are using Discord. Line and Facebook, okay? Social network and communication. Dota 2, okay. Okay, you know what? Yuntong is playing the same game. Media, let's see. Google, okay, a browser, so you browse the internet a lot. Line, you use Line also on PC. Discord and YouTube. Genshin Impact and Honkai Impact. Oh, okay, so lots of impact here. Genshin Impact, very interesting. Xuan, YouTube and Messenger, all right? YouTube and IG, okay? So on the mobile platform, I see typically IG, social network, and YouTube, video application. Oh, you play also Brawl Star. Don't starve together. You don't play with, okay, with Wei Yun, I guess. As team or as opponents against each other? What game do you play? Oh, Polly doesn't have time to play a game. But because of doing some research, some projects recently, Polly played a little bit of Pokemon Go. It was kind of fun. So we are particularly interested in the AR aspect of the game. Discord and Line for Team 7, Liang Zheng. IG and Netflix. Again, right? Social network and video. Okay, CSGO and GTA 5. Okay. So CS, I know it's shooting game, but I don't know much about the Go version. Polly used to be a hardcore player, but that's when she was in 20s, but not now. Sorry about that. And you can probably see why, Youyu, that Polly feels like, traveling. Netflix and Twitch. Oh, okay, so Zewei, you are very video-centric here. All right, so both are video-based. And Twitch is game streams mainly. Line and YouTube, again, video. I guess why you choose to take Polly's online course. So you're used to watch video and take information through the internet. I think that's a great ability. That's a skill, I think, these days. Line, LOL, and Valorant. So I think LOL is also strategy / action. Yeah. Let's see, Team 5, Weixiang, Netflix, and Line. All right. Instagram, Facebook. Okay, Weixiang, you are obviously very, very social. Okay, both are social network apps. LOL. Fall Guys. Don't know about this game, but the name is curious. Keke is also very video oriented. Line and Twitter. All right. Twitter. Interesting. Not many Taiwanese go on Twitter. Genshin. Oh, okay. So I think I saw somewhere. Amelia played this, right? Genshin Impact. Umasu. I don't even know how to pronounce this. Umasusume. It might be Japanese. And Youyu. Oh, NTU mail. 幼语, you sounded like you are a professional. No, not exactly a student. Messenger and Instagram, okay? But on the other hand, very social. Brawl Start also. I guess this probably is one of these, sort of time-killing games. A little bit of strategy, puzzle solving, maybe. Genshin Arc Knight. Okay, very good. Got it. Thank you for sharing what you guys are doing. I see, however, predominantly audio, video, communication apps like text or audio based or video based, and then social network. You see, multimedia and social networking, a lot more than web browsing, a lot more than email. So I see probably only 2 students saying that they spend more time doing email or web browsing. Very good. That's a good start. That means also that you guys are very familiar with all sorts of applications that we're using over the internet. Okay. Now let's talk a little bit more what are being done underlying these applications. Okay, and let's start by talking about the architecture before one can design an application. Okay, so one needs to think about, hey, how am I gonna, implement, form the game? Okay, there are information that the server needs to provide, or the game company needs to provide, or the video company needs to provide. Okay, are we gonna do it in client server or P2P or what? Okay, and that's the next video. The first thing we decide designing an application is its structure. There are 2 major models, client server and P2P. The third kind here is the hybrid of the 2. This is usually for bigger services where part of the service fits better running in client server model and the other part running in P2P. The client server model is straightforward. There are 2 ends. One is server, the other end, the client. The server is one of these powerful machines that's always on, running on permanent IP address so that they are always reachable. Now, given the scale of the internet service today, instead of using just one physical server, we need multiple of these, and they are housed in one of these data centers, so that we could serve thousands and perhaps millions of requests at the same time. The clients are you and me. We are lower-end machines and scattered around on the internet, communicating with the servers, requesting services from the servers. Now, unlike the server that are permanently connected, permanently reachable, we're moving around, only intermittently connected. This is because as we move, we might be assigned dynamically a new IP address. So our IP addresses are not permanent. So using one IP might not reach us at another time. So that's why we don't see clients directly communicating with each other. And we see 2 examples on the left here. So someone in the car might be trying to find the driving direction. So that could be a request to Google Maps server and getting the direction back. Now this could be a student trying to look up PA assignment. So a web request to the web server and the web page or the PDF file returning to the client. In the P2P model, we no longer have the always-on servers. In fact, all these end systems would directly communicate with each other and treat each other equally. So in this P2P world, think of it this way. Everyone is born equal. So the equal peers will request services from each other. They also provide services to each other. So such a characteristic is called self-scalability, because as we join such a P2P service, we ask for services, but we also open up our resources and adding new service capacity. Now, the only drawback of P2P is this. Hey, the peers, they are all intermittently connected, running on dynamic IP addresses. How do we ensure a P2P services is going to stay connected all the time? Yeah, the management of these peers is the complex part. The third model is using a combination of the former 2. This is usually used by bigger services where there are service components, and some component better run on client server and the other components P2P. Now, Skype is one such service. The component in Skype that's tracking your contacts and where their current IP addresses are is in client server mode. That's called the directory service. So the central directory server allows you to find the IP addresses of a remote contact. Once you decide to call someone, the calling service runs in P2P mode. That IP address is used by you to make the P2P direct call. All right, so that was the easy part. First, decide the architecture of your app. Second, decide what socket you're going to use to send data for your app. To implement a network application, it's equivalent of allowing process-to-process communication. Okay, so in client-server's case, a client process communicating with the server process. In the P2P case, peer-peer processes communicating with each other. Now, take note, the server process, remember server is the one that's always on, right? So server process is always started early, since the beginning of the service. Only when the service is started, then you call that the service is available. Okay? And it's always there waiting to be contacted. The client process is the one after being started by the user, initiating communication to the server and getting something back from the server in return. Now in P2P paradigm, the exchange between the peer processes are then a little bit complex. Each peer process will have the client side and the server side implemented. Okay? The difference is that this peer process client side contacts the server side of the other peer and vice versa. But either case, process-to-process communication. This is how you enable network applications. Now, let's take a step back and review. What is a process? It's a program running on a machine. So in fact, for two processes on the machine, there are occasionally the need to communicate with each other. Okay, this is possible and enabled by this set of API called Inter-Process Communication API. This is defined by every operating systems today. And this should be covered in the operating system course. Now, in case you don't have this, you might want to look it up a little bit, IPC. Now, in this course, we talk about process communicating with another process that are on different hosts. So two processes exchanging messages on different machines. How do we do this? We do have another set of APIs defined called the socket API that allow us to do this. If you call the socket API, a socket is created and associated to a process. And that's when the process can begin sending, receiving messages through the internet. Now, think of a socket as if there's a door. On one end of the door, the sending process pushes messages out. The other end of the door, we have the transport infrastructure. So let me explain with the picture here. Sending process here. Sending process pushes the message down, reaching the transport infrastructure. So the infrastructure here will move the packet further through the internet and come to the receiving end of the infrastructure. From here, messages go through the receiving socket and reaching the receiving process. And you see, process-to-process communication enabled by the socket API. Now let me draw your attention here. From this line and above, this is application layer. Everything running here needs to be controlled and defined by the application developer, application designer. So it includes the functionality of the sending receiving processes as well as the kind of socket we want here and here. Hey, why is it challenging? Because the transport infrastructure, there are actually multiple type of services being provided. So in order to call the socket API creating a socket, one need to know which transport protocol to choose. This depends very much on the kind of applications you're designing. You might also define additional parameters so that a process is correctly associated with the socket. One very important parameter to define before creating a socket is called the port number. So the port number, you can think of it as a unique identifier for a process running on a machine. So keep this in mind. And now let's take one step back and think about why we need a port number. All right. So let's see how we uniquely identify a process running on the internet. Well, first is, of course, try to find the machine the process is running on first. How do we identify a machine on the internet? Yeah, we do have IP address. You guys should all have heard about IP address. It's a 32-bit long number. With this IP address, we identify a machine. the question here is, does the IP address allow us to identify a process running on the machine? Having just the IP address, is it sufficient already? I know what you're thinking. You're probably thinking, no, not quite. If there are multiple processes running on the machine, then you cannot see exactly which process, right, we're looking for with just the IP address. Therefore, in order to identify uniquely a process running on a machine, we need something extra, the port number. So for a process running on the internet, in order to uniquely identify it, we need the IP address plus the port number. Okay. So a few example port numbers. For example, HTTP server, this is to support World Wide Web. It typically runs on port 80. So the socket connecting to HTTP server is on port 80. For mail server, port 25. It's a very common practice on the internet. For these very well-known services, we use a fixed port number so that it's easier for the programmers to remember. So that is also saying to send a web request, which is a HTTP request, to a server, gaia.cs.umass.edu. We send that message to here, or that socket is defined by this IP address and this port number. So this is the IP address of the web server, and this is the port number of the server process running there. All right, so that was a socket. Next, we decide what messages we want to send. So in order to send data, you kind of need to define the format and exactly which field is putting the message somewhere. Okay, so it can be slightly complicated. Now we have socket created connecting processes, we can begin to send messages. But you see, what we're talking about here is general application design. So an application can be a little bit complicated. The server could be providing multiple services. So how do we know, right, when the server receiving a message, the client is asking for service 1 or service 2 or service K? And vice versa. The server could be sending a message back to the client. And how does the client know what is the intention of the server? The messages being exchanged between these two processes need to be clearly defined. So that includes the type of messages. So one may be sending a message for a certain occasion. So there could be multiple types of messages defined for an application. Now use World Wide Web as an example. The client typically sends web requests, and the server sends web response. And inside the response that contain the web page the client is asking for. Now, continue to use the World Wide Web as example. Inside a web request, there'll be some fields, okay, we define. For example, time of the request, browser of the request, or language preferred by the user sending the request. Okay, so there'll be fields like this with the values that will contain in the web request arriving at the server. Server knowing the syntax, okay, of the request message will understand exactly what's going on the client side, and therefore send the most up-to-date web page in the preferred language, for example. Now, we also define semantics of messages because, again, using World Wide Web as example, the web response a lot of times sends back, for example, status. Okay, so this is the status of the request. Now, if the client is looking for an object that's no longer existing on the server, you see very often a response coming back saying 404. Yeah, what that meant is object not found. The web page is not found. So 404, that status comes with a meaning. Okay, so we define also the semantic of some of these code words. Now, this is really nice to send code words because you use few number of bits instead of sending longer English strings. So meaning of the information in the fields. Now, of course, right, this is almost like defining a language. Yeah, the rules, the timing we send the message, and when we receive a message, what kind of message we generate next. Okay, so all four together, the types, the syntax, the semantics, and the rules of corresponding back and forth between the processes. That's called the application layer protocol. So each application defines its own application layer protocol, defining the messages it requires, and the syntax, semantics, and the rules of exchanging the messages. Now, many of these application layer protocols are open, meaning if you just Google, you identify, for example, the World Wide Web's application layer protocol. That is actually called HTTP, and it's defined in one of these RFC documents. So So these protocols are open such that if I want to come up with my own browser, because I know, hey, HTTP requests, what the format should be like, the syntax, semantics, and rules, then I can write a browser such that it behaves just like the other browsers following the same RFC document. Same for email. Okay, so these open protocols are nice out there because each one of us can develop independently a new web browser, a new email reader, a new web server, a new email server. Now, many of the applications are commercial, owned by companies. So they do have their protocols, but they are not open. So these are the proprietary protocols. For example, Skype, we talked about using the hybrid model to communicate. It's got its own set of messages and syntax and semantics, but they're closed. It's hard to come up with our own client, a Skype client, such that it works with the legit Skype clients. All right, so these three design components, architecture, which socket you will use, and you need to design the message format and the exchange rules of these messages. Those are the basic component. Now, the next parts that we'll be talking about, including the rest of the 7 minutes and next week, is, if you recall, we need to call and establish a socket. But one aspect in deciding how to call the socket is also to define exactly which type of socket we want, because there are multiple transport layer services. Now, in order to decide which transport layer service we want, we need to know what is the application, and do we prefer applications such that the messages are sent without loss, or it's okay to have some packet loss. So having loss or not, it's one of the quality of service this application is expecting. That's because the users might be expecting this application to perform certain way. Okay? And that is called the QoS, quality of service. So with the next video, that's a little bit short, just 2.5 minutes, let's introduce QoS. Now, in order to know what is the right transport layer service for an application, we need to think a little bit more about the application we are designing. What is the nature of the content we're sending, and what the users might be expecting. The first criteria is called the data integrity. This concerns whether the data needs to arrive without any loss. The key word here is that if the apps are about sending text-based content, for example, a file, for example, a web page, for example, a text message, then users are expecting 100% reliability. If we're sending audio video, it's okay to have some loss. You know, think about speaking a sentence. If we miss a syllabus here or there, the listeners being human beings, we are intelligent. We can still make up the full sentences or make up for what the speakers want to say by looking at the context before and after the sentence. Second criteria, growingly important, timing. This is especially the case for interactive applications. So the key word here is interactive. Internet calls, live video sessions, or shooting games, interactive games. Users are indeed expecting low delay. Okay? And you guys know. Third is throughput. Okay, this is sometimes referred to as bandwidth requirement. Nowadays, we send multimedia content, audio, video. Text-based content, it does not require too many bits to send them, so it's not an issue. But for video and audio, we do need a substantial amount of bits per second in order to deliver them, so that the bits after recovery, okay, is in good quality. So if you compare video versus audio, the throughput requirement for video is higher and audio lower. Text, much lower. So we need to somehow guarantee a minimum amount of bandwidth in order for these audio-video communication to be effective. Text-based applications are elastic apps because there's no strict bandwidth requirement. The requirement is elastic. Fourth criteria, security. This is probably nowadays the most important criteria. Are the users expecting we are sending data such that we are protecting their privacy? Okay. So these four criteria together, we actually give it a special term. They are also called the quality of service. So before we can define what transport layer protocol we use, we need to think through what kind of quality we will be providing the application service. All right, so that's break open the next topic, QoS. Therefore, we can decide what the transport layer protocols we choose, okay, for the socket. And that's all for today. Next week, we'll continue to talk about QoS by showing a few examples, how you decide for a particular app, what is the QoS requirement. And given that, you will be able then choose what the transport layer protocol you use to specify in your socket. Okay, and all these you will exercising the PAs, the programming assignments. All right. Good. With that said, I'll see you next week. If you have questions, feel free to type them up on the chat. Okay, and following the lecture is the office hour. So Polly is going to be also on the Google Meet here. Okay, so feel free to just pop in and ask questions vocally or type things up on the channel. Okay, Polly would end the stream in a couple more minutes because it's not quite yet the end time of the lecture. Okay, so if you join the Google Meet between now and 12:10, hope you don't mind that showing yourself to the rest of the world, because these YouTube streams are all public for everyone to watch. Good. So let me play the background music as Polly grade also the quizzes. I see that you guys added more. Okay, so I see Jiake here. So maybe I can go on to the Q&A. So I see Keke's teammate, okay, added that he plays Elden Ring, and that is actually a game that I see adds a lot these days. It's probably a new game. Yeah, of course. Thank you, Youyu, for the very interesting questions. Okay, and of course, thank you. Liang Xin. Okay. Oh, Yun Tong. Oh, yeah. So, but I think I suck also playing many of these shooting games. Okay, yeah. So definitely maybe Wei Yuan can carry me if one day I go on Valorant to play a little bit. Oh, by the way, about gaming, I used to play the video games a lot. So these are the home video games, such as the Nintendo systems. Okay, but I actually downloaded some emulators that emulates these very old Nintendo machines. So I love playing the RPG games because playing them is almost like reading a novel. Because there's a story. Some of the stories can be very intense and extensive. And because you need to physically, seek things and battle, so it's even better than novels sometimes, because you also take actions. So you get, it's a little bit more immersive, okay, playing a role-playing game like that. There's a script, okay, and the later role-playing games can actually allow you to develop freely how you would like the characters go. So in the winter break, oh man, this winter break is just too short. So Polly finally get a week time playing the old games. I use an emulator that emulates Nintendo's family computer. And I played the very, very old RPG game called the Dragon Quest. For the American players or European players, it's called the Dragon Warrior. So I don't know if you guys heard, there's actually a community doing retro gaming. So this is a community of people like me close to retirement. Because when we were younger, even though we enjoy playing these games, much like we enjoy reading novels, books in general. But because our education system is this, after the high school, we kind of need to spend more time focusing on doing assignments, doing well on the exams, making sure that we satisfy parents and teachers' expectation. And we therefore have to abandon playing these games because there's not enough time. And so Polly would like to use free time also to try to make sure that she go back and not miss these games that previously she couldn't play before. So yeah, retro gaming. And good, so bye, I guess. Go on and catch lunch. Okay, bye Justin, bye Shenhai, bye Catfish, bye Yujie, bye Sean, and Wei Xiang. Who else? Oh, Yun Peng. Hey, don't mind, don't mind Wei Yuan too much. He's definitely just teasing you. You must be a very good friend, otherwise he won't do that. Zhong Ting and Wei Ze, of course. Bye, and Ke, bye. GTA 5. Maybe I can look it up here. GTA 5. Oh, okay. Hi, Catfish. Maybe I should stop the stream before you talk. Okay, let me end the stream now.